The situation we describe up here, this line and this circle represent a ramp and a ball rolling down the ramp. This represents a ball rolling down another ramp. These ramps are not assumed to have the same slope. As a matter of fact, let's just assume though that you have a given acceleration on this ramp. We want to know what the acceleration has to be on the second ramp in order for the second ball to start when the first ball is halfway down and catch up at the very end of the ramp. The two ramps are assumed to have length L, both same length. The balls are assumed to be at the top of the ramps. We want to know, first ball gets halfway, we release the second ball. What does its acceleration have to be in order to catch the first ball just at the end of the ramp? Okay, in an exhibit of poor use of board space, we start over here in analyzing the question. So what's down here is going to come after what's up here. On the first ramp, acceleration is A1, which is constant. That's the acceleration on the first ramp. We're going to let x1 of t and x2 of t be the position functions. So what are our conditions on x1 and on the velocity? What are our conditions on the motion of the first ball, in other words? Well, the first ball is released at time t equals 0 from the top end of the ramp, which is implicitly then the position x equals 0. So x1 of t equals 0 is x equals 0. v1 of 0, the ball is released from rest. That's kind of implicit. I don't think I ever said released from rest, but I say they start. Okay, so from the context of the lab, that should be clear. So we know that v1 at t equals 0 is 0. So we release the first ball at t equals 0 from position x equals 0 with velocity 0. Then this a equals a1 is unnecessary. That was already stated. What do we get? v1 of t is going to be the integral of a1 dt, a1 being constant. The integral is a1t plus a constant. And we evaluate the constant. If t equals 0, we get v1 of 0, and if t equals 0, we get just c here, so c has to equal v1 of 0. So our v1 of t function is a1 of t plus v1 of 0, or just a1 of t, since v1 of 0 is 0. x1 of t is integral of v1 of t dt. That's 1/2 a1t squared, which is the integral of the a1t, which is your v1 function, plus another integration constant. Now this integration constant is not the same as this one. I'm using c here, I used c here. We're done with this c. This is a new c. We could call this c1 and c2 if we were using them, if we were doing two integrations at once without evaluating our constants. But since we're done with this one, we can use c on this one. Okay, well, very similar to what we had before. That's 1/2 at squared plus x1 of 0, because x1 of 0 equals 1/2 a times 0 squared plus c, meaning that, of course, this is 0. C then equals x1 of 0. So there's our function. And since x1 of 0 is 0, x1 of t is 1/2 at squared. One thing I didn't do in class that I kind of wish I had, might have avoided a little bit of confusion when we get on into the later analysis. I'm going to note that x1 of t is 1/2 L. What does that mean? That means the position is halfway along the ramp. Well, that occurs, x1 of t equals 1/2 L when t equals the square root of L over a1, which is very easily obtained because x1 of t is 1/2 a1t squared. We set that equal to 1/2 L. We get this solution. You should check that out yourself. And this then is what we call t halfway, the time when we're halfway down the ramp. If we're given L and A1, we can find the time when the first ball is halfway down the ramp. So this t halfway is something that we're going to know. that we can get at any stage after this point right here. Meaning, of course, that we know when the second ball is going to be released. Okay, well, let's look at the motion of the second ball then. Okay, x2 of t, what's the function x2 of t? We know that a2 of t is a2, which is constant, just from our assumption that the acceleration here is a2, that x2 of t halfway has to equal 0. What does that mean? That t halfway is the time when the first ball is halfway down the ramp, so x2 at that time is still 0 because that's when we release the ball. Okay? And t halfway is the time when the first ball is halfway, and we didn't have that before, but that's just this. What else do we know about the motion of the second ball? Well, that its velocity at the halfway time is also 0. So the position and the velocity at t halfway are both 0. Again, remember, t halfway is a number we will have determined by this point, so we actually know what number to put in here. Okay, so, or we could know. Okay, in any case then, v2 of t, by integrating, following the same procedure we had, is going to be a2t plus c. Now, we don't have v2 of 0 equals 0. We have v2 of t halfway equals 0. Of course, if this ball's sitting still, at the time we release this ball, v2 of 0 is 0, but we haven't started the acceleration phase, so this function doesn't yet apply at that time. This function only applies starting when the time is equal to t halfway. Okay, so v2 of t halfway then has to equal a2 times t halfway plus c. And what's the conclusion from that? Well, we solve this for c. And we, well, this has to equal 0, which means c equals negative a2 halfway, so that our v2 of t function is just a2t minus a2 times t halfway. At this point, it's useful to compare this with the function we had previously. We said this in class as well. We could factor the a2 out. We get a2 times t minus t halfway. Remember that our x2 function in the example we did just before this one had a t minus 10 seconds. Okay, now that function didn't necessarily represent a problem of exactly this point, this kind, but that just means that the second ball there might have started 10 seconds later than the first. This one starts t halfway later than the first. So at this point we have the v1 and v2 functions, and we could set those equal and see when v1 equals v2 already. But let's go ahead and set the whole problem up. We've got the x1 function. We want to get the x2 function. That's going to involve integrating the v2 function and applying the condition that x2 of t halfway equals 0. Let's see how that works out.